And now I would like to go to the algorithm part to further appreciate how the superposition and interference help us to get something useful. Deutsch problem, what is that? I have a function, f of something. It is a 1 qubit input. The input, so it's like a black box. Black box. Your input can be 0 or 1, and then it gives you an output. Now, do not think that this is something very simple, because it can be a very computational intensive operation. For example, IC chip. I want to check if there's any violation or any failure among this 10 billion transistor chip. The answer is 1 or 0. That's it. Right? Sometimes you even don't need to know which part it failed. I just want to know whether it failed or not. In classical computer, you may take a very long time, let's say 50 years to compute. Now, here is of course, there's exaggeration here, but now assume I have a function. This is a very simple function. It only takes 1 bit as an input, and then it gives you an output. For example, function A, FA. If the input is 0 or 1, regardless of the input, it always gives you 0. We call this a constant function. Function B is different. When input is 0, output is 0. When input is 0, output is 1. We say it's balanced in the sense that half of them are 0, half of them are 1. This is a subproblem with a larger problem called George-Deutsch problem. I forgot it's Deutsch-George or George-Deutsch. Yeah. But this is only 1 bit, right? So you can also have another situation whether this is 1 and this is 0, and it is still balanced, right? Or you always give you 1, no matter what is the input. And our goal is to know whether this function is a constant function or a balanced function. Classically, if you want to know whether a function is constant or balanced, you need to compute it 2 times for this input, 1 qubit input, right? You put in 0, see what is the output. Put in 1, see what is the output. Then compare them, you know whether it's a constant or balanced. Is that okay? That is the statement of problem, right? Here is just advertisement. There's another video that go into the details. But for quantum computing, we use only 1 computation. So let's see how it does. Before that, we need to learn another thing, which is, again, very confusing, is something called quantum oracle. Quantum oracle is just like an oracle. It tells you something, but it doesn't tell you everything. So how does it work? A typical oracle here is called exclusive oracle. Or exclusive or oracle. So you can treat it as a gate. So after all, every quantum operation, now you can recognize that it is just a quantum gate. It's just whether it's a simple quantum gate or complicated quantum gate, because all the transformation must be unitary, must be reversible. So you define it by what? Again, how it transforms the basis state. I give a basis state to it. Here is 1 qubit, 2 qubit. I give 0, 0, how it transforms. And that defines the quantum gate. So a quantum oracle is something you need to come up, and this is a difficult one actually, right? So people come up with very good algorithm, but they might not be able to create the quantum oracle efficiently. What it does is this: it has 2 qubits. One of them you call it X, another you call it Y. You go through this oracle, it's going to give out the output as the first qubit doesn't change, still X. But the second qubit is Y exclusive function of X. Remember, what do we want to know? We want to know f of X. But it doesn't tell us what is f of X. It only tells us what is Y exclusive or f of X. So this type of oracle, maybe you can create it easily, right? And then you can use it for quantum computing. But from here, you do not know what is f of X. And then it's just same as what we discussed earlier. We don't care what is f of X. We only want to know what is whether it's constant or whether it's balanced. And that's why quantum oracle will be useful, right? So here I want you to take it for granted that we can create a quantum oracle in which we encode the problem we want to solve. In this case, the problem we want to solve is to know whether f is balanced or constant. I don't need to know what is f of 0 and f of 1. I just want to know that whether it's constant or balanced. Okay? Now, so let's take a look. For example, a very simple example, right? This is like a fake example that you already know the answer, and then you create the oracle. If I apply 0, 0, based on the equation here, it's going to keep the first qubit unchanged, still 0. Second qubit is 0, exclusive or f of 0. Right? So f of 0, the function is encoded there. Now, if I have a constant function, here I assume that my function is constant and always gives 0. Then, of course, f0 is 0, right? F of 0 is 0. So 0 exclusive of 0 is 0, 0. So it doesn't change anything. If my input, if the basis state is 0, 1, then this is 0, 1, exclusive f of 0, because y is 1, right? And then again, I need to exclusive f of x. X is 0, so f of x is f of 0. Again, f of 0, because I know it's constant, so this is 0. 1 exclusive 0 is 1, so unchanged again. So if I do the same thing for the rest, you find that this an oracle that corresponds to a constant function that always gives 0 is actually just an identity matrix in this case. Right? But this is just an educational instructional example, right? So do not think that why it's so simple. The point is that how you find this oracle that gives you the f0 if the f is so complicated, right? But let's just understand in this way. Now with this, then what is Deutsch algorithm? What it does is that first we need to create a quantum oracle like we said earlier, right? That in your oracle, you already have the f inside, the function that you are interested inside, right? This is difficult to create. Then I prepare a superposition state. The superposition state, you find that is actually the plus and minus state. And the plus is what can you do get to plus? You apply Hadamard gate to a 0 qubit. How do you get to the minus? You apply Hadamard gate to one state. And you can get one state by doing a NOT gate, right? So you apply the NOT gate to 0, you get 1, and then Hadamard gate, you get the minus. So why do we do superposition? It's very simple, because we want to do quantum parallelism. Once we have this state, we are going to fit this to the quantum oracle. And because we have 0 and 1 in this superposition, then you will do the computation f of 0 and f of 1 at the same time. And after that, you will do the measurement. But we do it such that because of the way we come up with the algorithm, if it is a constant function, it always gives you 0 at this bit. If it is a balanced function, it always gives you 1. So you do the measurement, you find that it is 0, then you know this function is constant. You find that it is 1, you know it is balanced. Do you see that we are losing some information? We don't know what f is up to this moment. We only know whether it's constant or balanced. So in my opinion, in quantum computing, somehow is that there's a conservation of energy. You think that you get some information much faster, but quantum computing just let you go around the route to get a particular information, but you don't know the rest of the other information. In classical computing, you know it is constant, but at the same time, you know what is f of every input. But here you only know it is f, it is constant, but you actually don't know what is f0 or f1. You don't know whether it's constantly 0 or constantly 1. So that is the concept. I hope that you can get it, right? And let's dive a little bit more how this one will work. This is the superposition state I just said, right? We prepare this into plus minus by using Hadamard gate and NOT gate. Then we apply this to the quantum oracle. If you go through the math, you will see this. But don't worry. You will be able to track it if you do it carefully. But I want to highlight to you is from here, you see that I have all this superposition. And can you see that it evaluates f of 0, f of 1 simultaneously in parallel. And if this is a constant function, it means f of 1 is just f of 0. So not f of 1 is just not f of 0. And as a result, because of this, we go through some constructive, destructive interference. The first qubits always give me plus. On the other hand, if it is a balanced function, it means that f of 0 is equals to f of 1 not. Because f0 is different. Oh my God, I've been muting. Have I joined the... Oh, so scared. Okay, I see. Yeah, so when it's balanced, it means f0 equals to not f of 1, right? For example, if f0 is 0, then f of 1 is 1. So not f of 1 is 0. So they are the same, right? So you can group the term, and then you will find that eventually your output will always be minus. Okay, if you cannot see that, it's normal because it's very long. But I just want to highlight that in this process, we do parallel computation. You see that, right? F0, F1, they are computed at the same time through this quantum oracle because of superposition. And then based on their, whether it's constant or balanced, you will do some cancellation and eventually one of them will be always plus, one is always minus. And that is how we can quickly determine whether this is a constant or balanced function, right? So this, go back to what I taught earlier. Quantum states is so profound. You have so much state, 300 electron, you have 10 to the power 80 something complex coefficient. They are all useless to you because you cannot get them. They're so rich. But you come up with some smart algorithm. So you use it to help you to do the computation in parallel and tell you the answer you want to know. You really don't care the details, what f is. I just want to know whether it's constant or balanced. So by doing this, instead of doing 2 computation, I only need to do 1 computation, right? And of course, if this can be go to more qubit, then we can, in a Deutsch algorithm, you actually constantly only need to do 1 computation if the problem scale up. This is the best scaling. But there are other issues like the preparation and quantum oracle preparation. But that is a good example. Is that okay? Yeah. Oh, no, this is just example. It's 1 computation. Here is just saying that if it's a constant function, it go through this part. If it is a balance, then it go through this part. But it's 1 computation. Okay. Okay. Then, in that case, I think that's it. Let's just do some hands-on, right? Let's go to the, maybe I quickly just show you what we are doing here. Here is the IBM-Q. You can, this is the NOT gate. I just add identity gates to align it. Then we have the Hadamard gate. We know that the function I'm interested in is just an identity, right? The oracle can be implemented by an identity gate. This is useless, completely useless here because I already know the result, right? But I just show that if this is a identity gate, then I do the measurement, I always get 0. If I use the real quantum computer, sometimes I will get 1 because of error, right? And this is such a simple circuit, we still get this error. That's why nowadays quantum computer is still not useful, okay? Now, and for the tutorial purpose, so I will just show you how to do that. If you don't have the account, you will just Google for IBM-Q, right? And then you just go to quantum IBM Quantum Platform, and then you can create your own account. I already have my account, so I go to here, IBM Quantum Composer. This is good for if you are new to this, right? And I just go to home. No, sorry. I will go to a file, have a new one, right? And then I will start building this circuit, right? Here it has 4 qubits. The highest one is the least significant bit. So you will see that it is flipped from what I have. Let me show you later. But for now, I will just delete the other qubits. This is the classical qubit. It can be used to do the measurement of the quantum qubit and store the information there. I only have 2 qubits, so I reduce it to only C2. Right. So now if I go back to my slide, a cheat sheet, what I need to do is I will put the NOT gate at the least significant qubit. Here it is at the bottom, least significant qubit, right? But here it is on the top. So I just drag the NOT gate from here to here. And then I add an identity gate to the most significant qubit. So in order to align them, I need 2 Hadamard gates so that I can prepare them in the plus minus what I need, right? Then I need a quantum oracle. I just add this separator to make it nice so that you can see that for this particular quantum oracle can be implemented by just identity gate, right? This is a simple example, right? I just put here. And my final goal is to measure the most significant qubit, but I want to measure in the C basis. That's why I have a Hadamard gate, because the output is plus and minus. I need to apply a Hadamard gate to rotate it back to 0 and 1. Then I do the measurement, right? So if we compare to this, I think I'm correct. And here it says it's going to store the qubit 1 information into first qubit, right? And then you just go here and then just run. But now you see that it's so difficult to run with IBM-Q, right? They have like 1,000 on the 9 for the real quantum computer, right? So I will just only use the simulator. And then I just click the run on simulator stabilizer. And then it should, here on the top right, it says it is running. I come here, click on this composer job. I don't know what happened. Okay, so now it's submitted, and then it has new job results. I click on this, right? It says it is completed. I do want to show you something. I click on this, see more details. First of all, it gives me the result is 100% 0, 0, which is correct, because 0 indicate this is a constant function. Okay, now there's no error because it's simulation. But I also want you to see this, but it's not in this case. You set up a circuit, it actually will do some compilation, become a transpiled circuit. Here turned out to be exactly the same. It will try to optimize. It's just like if you know IC chip design, sometimes you will just put, let's say, adder or a 3 input LAN gate. It might actually make it into a cool 2 input LAN gate. If it thinks that gives you faster speed or smaller area. So same here, it will try to optimize to more primitive gate so that it can run there. Right? Again, what is gate? Gate is not really what you lay out with transistor, right? It's just the microwave pulse and laser pulse. They just change it to the appropriate one, right? This morning, I actually submitted a job at 11:14. Looks like it's still in the queue. So, but anyway, I might have, let's forget this. So this is a way that you can run on the real quantum computer using IBM-Q. And it also gives you on the right the corresponding command that you can run from Jupyter Notebook, which I will show you later. Okay, so any questions for the Deutsch algorithm? Yeah. This one is something like not much of a practical example. So I mean, example is Actually, I don't know much. This is more like educational because it actually gives you the best speed up. It's just constant, even you keep increasing the qubit. But there are other limitations making it cannot achieve the goal.
I don't like exactly this algorithm, but this type of algorithm.
Oh,
some property which we need to know either.
Oh, I see what you mean. Actually, I don't know it well, but I'm pretty sure in computer science, many of the NP hard problems can be transformed or break down into simple problem like this. For example, traveling salesman problem, not for this one, right? You can break down into coloring problem, free set satisfaction problem, right? How do you color all the nodes so that no two colors are connected together? So I don't know but which problem, but I'm pretty sure some difficult problem can be transformed into whether this is constant or not. And a naive way, as what I said, can be, for example, if you have a chip, you want to see whether the test vector, right? You test the chip error, whether it's always constant or balanced. But no, so my example is not good. But I'm pretty sure you can transform, but I don't know. Okay, thank you. Okay, good. Any other questions? Sorry, cannot answer. Okay, but my goal is not this. My goal is want you to try IBM-Q. Okay, so then let's go to the part 4 about quantum Fourier transform. Again, I will go a little bit faster, but the point is it's not difficult if you agree with what I said earlier, right? So quantum Fourier transform, if you want to learn it, it's just discrete Fourier transform. But I particularly want to point out one thing is the nth root of unity. If you take, if you ask, right, what is let's say 1 to the power 1 over n, right? It is not just n. It can be equals to e to the power, right, I 2 pi m divided by n, because this all give you 1. And if you look into the complex plane, it is like along this unit circle, you subdivide them by n, and each of these points are the answer. Okay, so this is a complex math, but we don't need to really do it now, but I hope you recall what you learned before. Right? That's why I want to say this, because now if you do a summation of this nth root of unity, for example, I add up all these points, what would they be? It is just like vector, and they are evenly distributed. If I add up all of them, it will give me 0. And this is like destructive interference. If I can come up, make this as the coefficient of the basis vector and do some manipulation, they will just cancel all the things that I don't want. But if I have an equation which is not nth root of unity only, but to the power q, but with q equal to 0, I do something. Then it will sum up to n, a big number, right? So we don't go into the math, but I just want to remind you, the reason is the important thing about this is the constructive and destructive interference. Let's look at quantum Fourier transform. But before that, let's look at discrete Fourier transform. They are very similar. I have a vector x. It has n components, capital N, x0 to xn. For example, here, in electrical engineering, we have the value at t0 all the way to tn minus 1, right? x0. Let's say they're constant. So it's a DC signal, right? All of you know that if I do a Fourier transform, I will get a peak at frequency equal to 0, right? And indeed, if you construct a matrix, you see that I can transform this to here through this equation. Again, my goal is not to ask you to understand this equation at this moment. I'm sure you understand, just look at each symbol very carefully, right? Or if you have a copy of my book, I explain very clearly. But the point is this matrix is can be written as the nth root of unity, the omega here. Omega, which is this point, and then omega to the power 1, omega to the power 2. You can be written as this to the power of negative row times column. this is 0th row times 0th column, 0th row, first column, 0th row, n-1 column, and -1th row, n-1 column, right? The only message I want you to get is the power of the nth root of unity in this transform matrix. And why this is important? Because quantum Fourier transform is the same as discrete Fourier transform. The form is exactly the same. But now, remember when we say quantum gate, it is just a what? It is just the rotation of the basis vector, right? Or rotation of the superposition of the basis vector, which is a general state. So this is kind of telling us how it's going to rotate the basis state to another basis state. So in discrete Fourier transform, very often in our engineering application, we say we transform from time domain to frequency domain. But here we are not doing from one domain to another domain. We are still working on the basis that we have, the qubit space. Let's say you have 2 qubits, you have 0, 0, 1, 0, 0, 1, and 1, 1. And the quantum Fourier transform, what it does is just transform 0, 0 to something else, 0, 1 to something else, just like a Hadamard gate. Right? It just tells us how it rotates and transforms the basis state, still within the space that we are working on. The easiest thing to think about is 1 qubit quantum Fourier transform turned out to be the same as Hadamard gate. So isn't that Hadamard gate? You transform 0, 1 to plus state, which is 1 over square root 2, 0 plus 1. And then you transform 1 to the minus state, which is 1 over square root 2, 0 minus 1, right? So again, what it does is that it transforms the coordinate, the basis state. Okay, you can think of not a good analogy, but just like transform the head of the coin to make it spinning. So you have half chance to be head and half chance to be tail, like what we said at the beginning, right? We said a spinning coin is just like superposition of head and tail, right? So that is the gate, right? 2 qubit matrix will be more complicated, but it is just follow the equation, then you will get it, right? Since not all of you are doing the exercise, so I am going a little bit fast, but let me show you. Let's go to the Google Colab and see that how we can make a quantum Fourier transform gate. Quantum Fourier, yeah. So if you go to the end of this, right, I'll ask you to implement an n-qubit quantum Fourier transform. This is not easy, so we'll just see how we do it. And basically what I did is you start with, say, how many qubits you want. Here I say 3 qubits. But my goal is to do it automatically. So what we did is first, what's the size of the matrix when you have 3 qubits? 1 qubit is 2 by 2. 2 qubits is 4 by 4. How about 3 qubits? 8 by 8, very good. Because square exponential. That's why it's 2 to the power n, right? The size of the matrix. And then I just initialize a matrix with capital N to the power small n, right? And it's a compressed matrix. And then I go through the row and column. Then I say the elements at kth row and kth column is just equals to the equation here. 1 over square root n. And then just do the exponential. And this is just the nth root of unity. And then I, of course, multiply K and L, which is the row and column here. Okay, just very straightforward. If you don't see it, doesn't matter because I am going too fast. But the only message is that I just follow it, fill it one by one. So if you have time, you look at it carefully, you will get the same result, right? So if I run it, it gives me a really big matrix, right? The reason it's so messy because it has error, so it don't give you exactly 0. But this is like most of them are like 0J, 0 compressed component. Okay. Now, so let me just show you a little bit about interference. So here I have a vector. I use 1 over square root 8 because I want to normalize it, so the length is 1. And then it has component 1, 1, 1, 1, 1. So it means that it has component for every components, right? I think it makes sense. It's useful to say again, because now you have 3 qubits. So what are your basis state? You have what? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, all the way to 1, 1, 1, right? You have 8 of them. Then I'm putting 1, 1, 1, 1. I put 8 of them, right? This is 8. It means I have components of all of them, right? It's a superposition of all the components. I can rewrite it this as 1 over square root 8, 0, 0, 0, plus 0, 0, 1, all the way to 1, 1, 1. Is that okay? This is just one vector, one particular vector in this 3 qubit state, right? So that's why I created this one. And although this one looks messy, it's just because this is times 1 over square root 8. Then I multiplied this by the quantum Fourier transform gate I created, which is complicated 8 by 8 gate, right? I get this. The output is basically 1 at the beginning. And then this just e to the power minus 17, essentially 0. This is just the numerical error in the collect. They are essentially 0 for all of them. So you see that in this case, I apply a quantum Fourier transform gate to this constant vector with equal superposition. I get a constructive interference for the 0, 0 state, 0, 0, 0 state, and destructive interference for the rest of the state. Maybe useless for you now, but I hope you can appreciate that if I can incorporate this in some algorithm, do something, come up with something smart, then I will be able to create some useful algorithm. For example, HHL. HHL, or quantum phase estimation. This is another algorithm. HHL use quantum phase estimation, and quantum phase estimation use the quantum Fourier transform. They all rely on quantum Fourier transform to do some special operation and then do the constructive and destructive interference to single out the results I want. And because they're so smart, the HHL, it will actually help me to solve the system of linear equation exponentially faster. But there is a catch again. Once I get the result of my linear, so I want to talk about this, also very important. I mean, as hope you can get home with this, right? Take home with this. I want to solve this system of linear equation. This is a n variable. Let's say 1,000, 1 million equations. It's split up by log n. Then if I have a 1 million equation, maybe you can say, oh, I now only need 1,000 units of time to do it, right? A great speed up. But I have 1 million solution. How are you going to read 1 million solution? Isn't that you need the n order of, at the time, the order complexity of n to read it? Even the reading this n this data, you take 1 million units of time. So even you speed up by 1,000 times, right? No, 3 times, sorry, log 6, sorry. Log 1 million is 6, right? You speed up a lot, right? But by just reading the answer or preparing the input, it already takes you 1 million units of time. Then this algorithm becomes useless, right? So then you then think of it, how will I use this output? I cannot just use it by, I want to read all the answer and then use up for other computation. One possibility is that can you come up with a machine so that you just use the output to take the FH value because you are only interested in the expectation value of a certain measurement. Then you can just apply this wave function to that. Maybe you don't understand what I'm talking about here, that's okay. But just think about the speed up is so fast. Only 6 units of time because log 1 million. But by reading the answer, you already need 1 million of units, right? So you cannot use it directly, right? So these are all the catch in quantum algorithm that you need to be careful about. Okay, is that okay? So if that, so that's it for the part 1 to part 4. We have done we understand superposition is important. We know what is entanglement, and we know measurement is important, right? That they are so profound, I cannot get all the information. And we see that if we